So far we've seen a couple of strategies for polynomial time algorithms. We've seen divide and conquer, and we've seen dynamic programming. Now we're going to turn to another classic strategy, namely greedy algorithms. What greedy algorithms do is they look at the current situation, how much of the puzzle or problem they've solved, and they take the step which in the short term looks like it will make the most progress. Of course, this kind of short-term strategy is a disaster for almost every problem that society faces, but for certain problems it actually works. So let's check it out. So a classic problem, an optimization problem, is called minimum spanning tree. It has a nice history. It goes back to the 1920s, when people were first starting to think about building electrical power networks to transport power to different cities. And a guy named Borówka, I hope I'm saying that right, who lived in Bohemia, was interested in figuring out how to do this in a way which would minimize the total length of all the power lines, or if you prefer, the total cost. Maybe for some of them it's harder because you have to go over some mountains or something. So he came up with the following greedy algorithm. He said, well, let's assume for a moment that we just need to make sure that our cities are connected somehow in a network. If we're not trying to make this network redundant at all, then we have no need for loops, because loops give you two or more ways to connect cities to each other. So let's just go for a tree, a graph which is a tree. If you think about it, this is actually a really bad idea for a power network. You want redundancy in case some power line goes down. But let's bear with him. So he proposed the following strategy to design this tree with the total, but to minimize the total cost of these links. Start by connecting the pair which is closest together. And now continue adding new edges, but always adding the shortest or cheapest edge, which doesn't complete a loop, because you don't need loops. So it might be that pair next, and then let's see, it would be that pair, and now we connect those two, and now those two, and now those two, and now those two, and now we're done. All the cities are connected. There's a path from everyone to everywhere else. Now this is a spanning tree, but why should we believe that this is the best possible spanning tree which minimizes the total length? In fact, for this particular problem, this greedy algorithm works. It succeeds in finding the optimal tree. It never leads us down the wrong path. So let's actually prove that. Suppose that this algorithm kind of wants to add this edge E because it's the shortest edge that isn't there yet, that doesn't complete a cycle or a loop. But suppose, for purposes of argument, that the actual spanning tree contains some other edge, E prime. Well, the thing is that in order for this to be a spanning tree, it has to provide some path, which might go through E prime, from one of E's endpoints through to the other. Well, if that were the case, imagine adding that edge E, the one that the algorithm wanted to add. Now you have a spanning tree plus a single loop. But then you could delete E prime and get a new spanning tree, but because E is shorter than E prime, the new spanning tree is shorter. So what we just proved was a proof by contradiction, that in fact adding the shortest edge can never lead you wrong. Now, again, this doesn't work for most problems. I mean, imagine playing chess. It's often a good idea to sacrifice a piece because 10 moves later it's going to put you into a better position. I'm not actually that good a chess player, but that's what I'm told. So for most problems, you need to look ahead. You can't just do what seems right now. So let's look at the traveling salesman problem, the Willy Loman problem. So here we have a bunch of cities to visit, and we again want to connect them, but not with a tree, instead a path. If you think about it, a path is a tree if it doesn't have loops. It's just a tree that doesn't branch. It's one long stringy tree. So in fact, the traveling salesman problem, or as I prefer to call it, the traveling salesperson problem, is just a more constrained version of the minimum spanning tree. Now suppose we start out in this particular city and we want to tour all the cities. Well, a greedy algorithm would go at each step to the nearest city that you haven't visited yet. That would lead us down this path, and then we'd say, oh no, we need to go all the way back to this other city that we skipped. We made a huge mistake. What we should have done was be less greedy and be willing on our first step to make a sacrifice, to go to a city a little bit farther away than the closest one, and that would have decreased the total length of our tour. So the traveling salesman problem is one where the greedy algorithm simply doesn't work, unlike minimum spanning tree. In our next video, we'll talk about what is it about a problem that makes the greedy approach succeed or fail.